Good afternoon, everyone, and thank you for attending our Flex and Rigid Flex PCBs Technical Issues and Datasets webinar. My name is Ryan Wood, the Content Marketing Manager here at Epic. Before we get started, I just want to let you all know that you'll be muted during the presentation. If you have any questions as we move along, please enter them into the questions panel, which is located in the webinar control panel, and we'll try to get to all of them at the end of the presentation. If we don't have time to go through all your questions, we'll be sure to reply back to you by email. Also, we will be recording this webinar and we'll be posting both the recording and the slides on our website and YouTube channel. Our presenter today is Zachary Walker, our Product Manager of Flex and Rigid Flex Circuits. Zach's main responsibility involves interacting with customers' Flex and Rigid Flex products from start to finish. He assists customers in their product creation to ensure they can suit the customer's needs while still being manufacturable. Zach addresses concerns or issues that may arise during any part of the process. He also oversees the quoting process for Flex and Rigid Flex PCBs. Zachary came to Epic with 3 years experience in the production and planning side of circuit boards. He's familiar with aspects of production involving engineering and manufacturing, and has a bachelor's degree in chemical engineering from Texas Tech University with minors in chemistry, mathematics, and polymers and material science. So without further ado, I'll pass it over to Zachary.
All right, thank you for the introduction, and thank you everybody for joining us today. As he said, we'll be going over the technical issues and data sets for Flex and Rigid Flex PCBs. Now, the main challenge comes with these parts is that Rigid Flex and Flex circuits have numerous design requirements that can either severely differ or not even exist for rigid PCB designs. Now, the biggest technical issues we'll end up seeing for Flex and Rigid Flex are IPC 6013 requirements, board and panel profiles, and Coverlay and solder mask capabilities. Now, these technical issues that we end up running into can end up creating significant delays and sometimes even result in complete redesigns if the problem is too widespread or if it becomes too major of a concern. Now, our agenda today, we're going to start by covering IPC 6013 items, starting with the correct callouts for materials, specifications, IPC QC and manufacturing specification, and epoxy strain relief specifications. We'll be then moving on to plated through holes and vias, where we cover plating requirements and then plated through hole and via to flex transition minimum spacing requirements. After that, we'll move on to mechanical requirements, starting with board and panel profiles, which consists of the part outlines, inside corners within part outlines, and then the breakaway tabs within Flex and Rigid Flex arrays. After that, we'll cover stiffener requirements and minimum sizes, and that'll wrap up our mechanical requirements. And then finally, we'll be covering Coverlay and solder mask, where we'll be covering combination usage, the minimum web capabilities for both of them, as well as the Coverlay shape restrictions. Now, starting off, we're going to start with the IPC 6013 items. And as I said, we're starting out with the callouts and specifications. Our preferred methods of doing callouts and specifications involves using the base common names of materials, such as FR4, polyimide, flexible polyimide, Coverlay, generic broad terms. Alternatively, we can use the IPC 4204 specification sheet codes, which we have to make sure in the process, though, that the correct up-to-date codes are used and that the proper code is used, or else we'll end up with misunderstandings. So as you can see to the right, we have some of the codes listed, whereas we have the 4204/1, which is for a copper-clad polyimide dielectric with acrylic adhesive. And as you can see, each slash code ends up specifying something different, whereas this /2 ends up being the same, except it involves an epoxy adhesive instead of an acrylic adhesive. Now, common errors we end up seeing with material callouts end up involving trade names, Kapton, DuPont, Philios, things of that nature that specify either a specific manufacturer or a specific material. These callouts can end up stopping quotation or production and end up causing large lead times or changes in pricing due to material stock availability, UL certification, and things of that nature. So an example of that is off to the side where we have the layer stack up, and you can see that here on the layer stack up, rather than calling out polyamide, they repeatedly called out Kapton, which is something we tried to avoid. Another reason is that not all material brands are available at all geographic manufacturing locations. A good example of that being DuPont. Since they're a North America-based manufacturer, it tends to not be available offshore readily. And another reason is there actually exists many other materials which will be equivalent to these ones in North America, but are not commonly known. Now, regarding IPC QC and manufacturing specifications, one of the main things we'll see is IPC 6012 versus IPC 6013, where 6012 applies only to rigid PCBs and 6013 applies to flex and rigid flex PCBs. There are numerous differences, but the key differences we see is the different plating requirements between both specifications, the callouts for solder mask versus flexible solder mask and Coverlay, and also how 6013 will detail many additional features that are specific only to flex or rigid flex, such as stiffeners, PSAs, pressure sensitive adhesives, things of that nature. Most often due to rigid PCB drawing templates being adapted to flex and rigid flex designs, we'll end up seeing different specifications that can only apply, such as minimum thicknesses, and again, the 6012 versus 6013. And so here is a good example of this, where the top is something we prefer to see. We see where they list out a polyamide Coverlay. They're using generic terms, whereas on this next portion, we see that they call out IPC 6012 Class 2. Now, again, like I just said, 6012 pertaining to a rigid PCB. This means that we then have to go back and clarify that this is supposed to be a flex or a rigid PCB. And then down at the bottom, you can see where they used generic callouts as well. So rather than calling out a specific Coverlay manufacturer or Coverlay product, they'd strictly call it Coverlay, Coverlay adhesive, and things of that nature. And then towards the bottom where they say polyamide stiffener, rather than using some trade name or specific product. Moving on to epoxy strain relief specifications, we do have some dimensions that are some minimums that are IPC constraints. The first of which is the minimum width, which is 1.5 millimeters. In addition to that, we also see the minimum flex to rigid height delta in the stack up, which is 10 thousandths of an inch. So what that corresponds to is the height of the rigid section to the height of the flex section can be no less than 10 thousandths or 10 mils. For epoxy strain relief formulas, we have stiff, semi-flex, and flexible formulations. However, we only use flexible formations when we're doing manufacturing. Commonly, those aren't called out, but we will occasionally see that they call out one of those specific ones. And off to the side, you can see it's kind of difficult to see here along this transition. You can see that black bead of epoxy strain relief. Moving on to plating requirements. Per IPC 6013 for flex and rigid flex, on a 2-layer flex, it's dictated to have an average of 12 micrometers or 472 microinches with a minimum of 10 micrometers or 394 microinches. This changes, however, when we get to 3 or more layers for rigid flex and flex boards, where the average then jumps up to 25 micrometers or 984 microinches with a minimum of 20 micrometers or 787 microinches. Common errors we run into is copper thickness callouts being incorrect for the layer count. So we'll see copper thicknesses for 3+ layers called out on a 2-layer or vice versa. And then also callouts for IPC 6012 plating, which does differ a fair amount from IPC 6013. So here at the bottom, you can see where we have the IPC 6013 plating guide, and we can see where it dictates type 2, a double layer, and then type 3 and 4, which are multi-layer flex and rigid flex, and how the plating goes up going from type 2 to type 3 and 4. Moving on to mechanical requirements, our number one thing we end up seeing is the part outline. Best practice is to include it in Gerber format. So for flex designs, that's going to be just the part outline. For rigid flex designs, we would actually need 2 outlines, one for the rigid sections and then one for the flex sections. If for any reason you can't provide it in Gerber format, we can work with DXF to then convert it to Gerber on our end. Common errors end up being that either a part outline is not included or it's missing the rigid outline. So we don't know where the flex and rigid portions are supposed to end and begin. And then another common error is where we receive the part outline in only PDF format, which is either near impossible or impossible to convert to Gerbers. And off to the side, you can see an example of a part that has both the flex and rigid outlines. So they've got the copper portions, but they've got the outline surrounding the copper. So on the left side being the rigid and then the right side being the flex portion. The next thing about board outlines that we end up seeing a lot of is the inside corners in board outlines. So best practice is to radius all corners of all areas, flex and rigid. We prefer a minimum of a 20 mil radius. So any of these areas off to the side, you'll see where it's the sharp corners will then be radius to 20 mils. These are rounded off to both allow for manufacturability and also to eliminate any stress concentrators, like for instance here at the transition area. Most common errors we see for these are sharp inside corners, which can't be done properly with typical laser cutting, or that we end up seeing too tight of radii, which ends up being almost similar to a sharp inside corner. Moving on to assembly arrays, we'll be covering breakaway tabs, where these are the tabs that are used here on the side. You can see that connect the board to the array, and they're used to ease separation of boards after assembly. These tabs usually contain what are called mouse bite or breakaway holes for rigid areas. You can see where it's got 3 little holes, and this basically helps to break away the area from the array rails. On flex, however, we do prefer to see solid tabs. And so moving on to common errors, it relates back. So either we don't have sufficient copper spacing from features to tabs, because tabs do have to be recessed into the part outline slightly, or we see breakaway tabs in flex areas that have holes that end up making it very easy for it to be damaged or mishandled during either manufacturing or assembly. And then this is another example of an assembly array with breakaway tabs. You can see we've got these rigid flex designs. This is a rigid region with all these breakaway tabs with mouse bites. And then this flex region is also suspended, but these tabs are solid, however. So moving on to stiffener requirements. Stiffener materials that we end up seeing end up being polyimide, FR4, stainless steel, aluminum, and of those, the most common are the FR4 and polyimides, which end up making a vast majority of the designs we see. For size and thickness, FR4 and aluminum share the similar characteristics, where The minimum approximate size for that is roughly 1/2 inch by 1/2 inch. Common thicknesses for those are also the same, where it's 0.5 millimeter and 1 millimeter. However, moving on to polyimide, the minimum size is very design dependent. So on some designs, we can go significantly smaller. On some of them, we can just go slightly smaller. It just all depends on what we see from the design. In this case, for polyimide, max thickness ends up being about 10 mils, which is about 1/4 millimeter. And then for stainless steel, our thicknesses that we commonly operate within is 5 mils and 8 mils. So you can see off to the side where, in this case, got varying stiffeners of all kinds going across this board and across the other board. Common errors we see for stiffeners are dimensions and locations not specified. So either it's not specified which layer the stiffener is supposed to be going on, where on the design that the stiffener is supposed to be located, or we have a drawing that just indicates a stiffener and never actually specifies a size. And without a file, we wouldn't know exactly where it's located, how it's shaped, and what it's supposed to cover and not cover. Another common error that we end up seeing is incorrect materials for applications, most common being for ZIF applications, which require a polyimide stiffener. We would end up seeing FR4 stiffeners. And then the last common error is undersized stiffeners, which will apply more to FR4 stiffeners, since those are the more common ones that we see, where it goes under that 0.5 inch dimension and thus becomes either impossible or too unwieldy to be able to apply to a design. And then you can see here that we have various details detailing stiffeners, detailing which side a stiffener is supposed to be on, and things of that nature, which is generally what we like to see. We like to see dimension drawings in addition to Gerbers, or at the minimum a Gerber for stiffeners. So moving on to Coverlay and solder mask. Starting with Coverlay. Coverlay is a solid sheet of polyimide material that gets applied on the outside of flexible circuits to encapsulate and protect copper with selective openings for pads. These come in 3 primary colors: natural amber, white, and black. Unfortunately, those are the only ones we can supply at this time. The feature openings for Coverlays are typically machined, so you'll see them done with laser cutting, drilling, punch and die, things of that nature, with minimum web thicknesses of 20 mils. This is because anything below 20 mils, it'll be excessively fragile. It could rip away from the other Coverlay easily during application, or even that it may bend or distort slightly and end up causing misalignment and covering crucial pads or things of that nature. Then we've got solder mask, which this is a liquid epoxy with an added flex agent to be able to be bendable during the lifespan of the PCB. These colors are a lot wider of a range than Coverlay. Generally, we can do many colors: green, red, blue, yellow, black, white, things like that. I've even seen wild colors like pink and purple, but those are very non-standard, and that does require a discussion beforehand to make sure it's possible and doesn't affect the quote too much. For solder mask, the features are photo imaged and chemically formed. It's a similar process to rigid PCBs in that aspect. It doesn't change much. It's just the additive that changes. For our minimum web thicknesses, however, it is significantly smaller than Coverlay. So for green solder mask, we will see a 4 mil minimum web, whereas for all other colors, we see a 5 mil minimum web. Common errors we see with solder mask and Coverlay both is one-to-one opening to pad size, where if you have a 10 by 10, 10 mil by 10 mil pad, we'll end up seeing a solder mask opening or a Coverlay opening that is 10 mil by 10 mil. We have a minimum oversize that we do require for both Coverlay and solder masks that differ. So in that case, it would be 5 mils over per side for the pads for Coverlay, and then for solder mask, it's 2 mils over per side for the pads. Another common error we see is thin webs for both Coverlay and solder mask. These are generally resolved by either decreasing opening sizes or gang opening features, which basically entails creating a rather large opening across multiple pads rather than individualized pad openings. Regarding combination Coverlay and solder mask, these are applied to flex designs with high density SMT components. This usually involves webs between adjacent pads being below the minimum 20 mil manufacturable limit of Coverlay materials. Usually flex solder mask is applied in these high density areas, as you can see on the right, and then Coverlay is used through the balance of the design. So you can see where we have these tight features, U4, U5, 6, and 7, where these features are so tight that we would not be able to do them with Coverlay. So therefore we did the combination of the mask over those selective areas with Coverlay through the balance of the design. So our recommendations for that are to supply it as one singular file for the Coverlay. Let us separate them out as necessary, because the alternative is that it's supplied in 2 files, which ends up becoming very messy to figure out what could be done with Coverlay, what could be done with solder mask, where to move things from one file to another. So ultimately, we just prefer the one file, and then we'll separate it out from there. Another common thing we see with Coverlay, so Coverlay has to be one continuous piece throughout the design, because, as I said earlier, it's a sheet being applied to the design and laminated to the panel. Issues we run into with that end up being extended tabs, where the tab will extend further out past the body of the Coverlay and end up turning or getting damaged and laying across copper, peeling back and showing excessive copper, things of that nature. We've also got isolated islands. These are difficult to manufacture, if at all, and these are, again, resolved by combination Coverlay and solder mask. Reason being, again, it's a solid sheet of Coverlay, so it's impossible to apply both the solid sheet and floating pieces of Coverlay throughout the board. And then the last thing we normally see is excessively long and thin webs. It's similar to the extended tabs. These can rip away from the body of the Coverlay and end up laying across copper, going somewhere else on the board where we don't want it, things of that nature. So we generally like to avoid the excessively long and thin webs whenever possible. So in summary, many unique elements and specifications for flex and rigid flex designs not included or not correctly defined in supply data sets. This ends up leading to conditional or budgetary quotes that end up, we have to go back to the customer and review, get approvals, and ultimately we'll end up slowing down both quotes and production times. We see brand-specific material callouts, which, if they're imposed, can limit supply chain, add excessive cost, excessive lead times, and even then, not all suppliers will end up being able to use some of those materials, either due to availability or UL certifications. And then finally, use of combination Coverlay and solder mask solution may be required sometimes due to high density SMT components, or in special cases such as islands and things of that nature.
Thank you, Zachary. Now, while Zach reviews all the questions that came in, I want to briefly mention some of the additional PCB-based products we offer here at Epic. For over 70 years, Epic has designed and manufactured custom build-to-print electronic products. Our expertise not only lies in printed circuit boards, but in custom battery packs, overmolded and other types of cable assemblies, flexible heaters, high reliability user interfaces, and AC fans and motors. Next slide, please. I also wanted to take a moment to mention Instant PCB Quote, our in-house quoting and ordering tool for PCBs. What many people don't realize is that you can quote and order flexible PCBs online. From prototypes, pre-production, and production volumes, we have many options available that can be done online. If you're not already an Instant PCB Quote user, simply go to epictech.com/instantpcbquote to get started and create your free user account. And now I'll turn it back over to Zachary to go through some of the questions that came in.
All right, thank you. And the first question we have, can Epic provide a copy of IPC 6013? Unfortunately, we can't provide any copies of IPC specifications. These specifications are copy protected. That makes it to where we can't share our copy of the specification. In that case, we generally prefer to guide people towards the IPC website to where they can then purchase the IPC 6013 specification. Okay, and are all polyimide flex materials equivalent? So all available standard flex materials meet IPC specifications and are UL certified. There are special cases, unique materials, such as ones from like DuPont that get rarely used in the industry or are very certain use cases. For instance, for the LF series from them, we'll see it's a non-UL certified legacy material, but we see those typically with qualified military and medical designs where they can't readily change the design. We'll see high temperature or HT polyimide based adhesive Coverlays. Those operate on a 200 degrees Celsius continuous operating temperature, very, very specialized material. Or there's a material, a TK material, which is Teflon polyimide hybrid. That's a high-speed material that's, again, in the name, high-speed, used for high-speed applications. And let's see. What if a square inside corner is required? A non-plated hole is typically put at that corner, approximately 40 mils at the center of that inside corner to help create that sharp edge. It's never going to be perfect. It's hard to get square edges with round lasers or round drill bits. So, but we can get pretty close by doing that non-plated hole there at the corner. It'll eliminate any of the remaining radius of material from extending from the outline once the part is then finally routed to shape. All right, and how do we determine what are effective stiffeners for a specific design? And that is kind of a tricky and open question because each design is unique to itself. Each design has specifications and requirements. So some designs we'll see that don't require any stiffeners whatsoever, while some require multiple stiffeners, like an FR4 stiffener here and a polyimide stiffener there. And so because of this, we end up having to go on it on a case-by-case basis and review in a call or from the drawing to see what the requirements are to then determine what effective stiffeners are and if we have any recommendations for the stiffeners. So good examples of that would be your component and connector areas where we'll use an FR4 stiffener, for instance. ZIF areas, which I had mentioned in the slide earlier, which use a polyimide, and then other special use cases where you might need a stainless steel stiffener, aluminum, and things of that nature. But unfortunately, I believe that is all the time we have for questions today. I wanted to go ahead and thank everybody for joining us today. And I believe if you have any further questions, you can contact us and we'll answer them in a timely manner. Thank you.